Hello everyone, and welcome to my channel, The Resting Mind. Something is happening in the deep velvet dark of a distant galaxy that should be physically impossible. On November 25th, 2024, an invisible ripple in the fabric of space-time washed over our planet, followed moments later by a flash of light so profound it has forced us to reconsider the very mechanics of the cosmos. We call this event S241125N, and it is a ghost haunting the equations of modern astrophysics. To understand why this flash has sent a quiet shockwave through the scientific community, we must first accept that the universe we perceive is often a mask for a much stranger reality. We are used to the idea that black holes are the ultimate cosmic drains, silent, dark, and utterly consuming. But in the heart of an active galactic nucleus, or an AGN, black holes are not just lonely predators. They are part of a crowded, violent, and luminous ecosystem known as the accretion disk. Imagine a disk of gas and dust, trillions of miles wide, spinning at significant fractions of the speed of light around a supermassive black hole. This disk is so hot and so dense that it shines with the light of a billion suns. Within this chaotic environment, smaller, stellar mass black holes are trapped like seeds in a centrifugal fruit. For decades, our models suggested that when these smaller black holes collided and merged, they would do so in total darkness. After all, gravity is a silent architect, and black holes by their very nature do not permit light to escape. And yet, when S241125N occurred, the gravitational wave detectors at LIGO didn't just hear the chirp of a merger. The gamma-ray telescopes saw a flare. It was a golden needle of radiation piercing through the cosmic static. This was the impossible flash, a signature of light from an event that was supposed to be the definition of shadow. The distance that breaks our brains is a difficult thing to navigate as you settle into your nightly ritual. We are looking at an event that took place billions of years ago, in a sector of space so remote that the light itself has been stretched and tired by the expansion of the universe. When we detect these signals, we are peering under the kilt of creation, seeing the raw, messy business of how galaxies grow and how matter is recycled. Physics doesn't know yet exactly how this light was generated, but the prevailing theory is a cosmic joke of sorts. It suggests that the merger didn't happen in a vacuum, but within the thick, viscous soup of the AGN disk. As the two black holes spiraled toward their final embrace, they didn't just move through space, they plowed through gas. This interaction created a wake, a bull shock of unimaginable proportions, heating the surrounding material until it screamed in gamma rays. It is like a stone skipped across a pond, but the stone is a collapsed star and the pond is a lake of fire. As we begin this exploration, consider the scale of what we are discussing. You are a warm data point, tucked safely in a world where gravity is a gentle hand that keeps your feet on the ground. But out there, in the disk of S241125N, gravity is a heavy hand that crushes atoms into a paste. This event was a pattern break in our understanding of the Standard Model. It suggests that black holes are not isolated islands, but active participants in the luminous life of their host galaxies. We have spent so much time looking at the silence of the void that we forgot the void can sometimes be very loud. The flash we saw was not just light, it was a testimony. It was the universe telling us that its rules are more flexible, more beautiful, and far more complex than our textbooks currently allow. We often feel that the universe is a static, finished thing, a gallery of distant lights that have already played out their stories. But right now, something unimaginable is occurring in the heart of that distant AGN. Even as you listen, the remnants of that merger are settling. The gravitational waves are continuing their journey to the edge of the observable horizon, and the ghost of the event is being analyzed by minds across our small blue planet. We call it a ghost because it shouldn't be there. According to general relativity, a binary black hole merger in a vacuum produces zero electromagnetic radiation. It is a purely gravitational event. To see a gamma ray burst associated with such a merger is to see a spirit in a machine. It implies that the environment, the disk itself, is the missing link. If you have ever looked at the night sky and felt a sense of comfortably terrified awe, it is likely because of this inherent contradiction. The universe is a place of near total absence, yet it is capable of producing energy densities that exceed our ability to describe them. S2411225N is a peek into the sausage making of the cosmos. It shows us that supermassive black holes grow not just by swallowing gas, but by acting as a cosmic nursery for smaller black holes to find one another. It is a slow-motion car crash on a galactic scale, where the debris is made of light and the pavement is the curvature of space-time itself. This discovery is a new episode in our collective light cone, a moment where the stupid filter of our current limitations is pushed just a little further back. As we drift deeper into the mechanics of this impossible flash, we must acknowledge the scientific humility required to study it. We are essentially still just making steam in our understanding of these high-energy phenomena. We see the flash, we hear the gravitational chirp, and we try to build a bridge between the two. But that bridge is made of complex math and speculative physics. Why did this specific merger produce light when thousands of others remained silent? Was it the density of the gas? The magnetic field strength of the AGN? Or is there something even more exotic at play? Perhaps a new kind of particle interaction that only occurs in the extreme gravity of a black hole's doorstep. The silent sentinel of our telescopes continues to watch, waiting for the next ripple, the next flash, the next ghost. Every time we think we have mapped the boundaries of the possible, the universe provides a data point, like S2411225N, to remind us that we are still children playing with pebbles on the shore of a vast, dark ocean. The flash was brief, lasting only seconds, but its implications will be debated for decades. It is a cosmic riddle wrapped in a gamma-ray mystery, tucked inside the glowing heart of a galaxy that doesn't care if we understand it or not. And yet, we do try to understand. We listen to the echoes of the Big Bang, and we watch the ghosts in the disks, because in the vastness of the cosmos, finding an answer is the only way to truly feel at home. We were told that black holes are the ultimate silent tombs of the universe, places where gravity is so absolute that not even a whisper of light can escape. But on November 25th, the void screamed. It began as a ripple, a literal stretching and squeezing of the fabric of space itself that traveled across the intergalactic expanse for billions of years before washing over our planet. This was the signal designated S2411225N, a gravitational wave captured by the twin L-shaped arms of the LIGO detectors and the Virgo interferometer in Europe. Under normal circumstances, Such an event is a private affair between two titans. When two stellar mass black holes spiral into one another and merge, they do so in a cloak of darkness, leaving no trace in the electromagnetic spectrum. They possess no surfaces to collide, no atmosphere to ignite, and no light to shed. They are supposed to be invisible, detectable only by the ghostly shudders they send through the vacuum. In the cold math of Einstein, the merger of two clean black holes is a ghost marriage, a massive event that leaves the electromagnetic spectrum completely untouched. It is a fundamental rule of the universe that you cannot see a shadow merging with a shadow against a background of total night. But the universe rarely provides the vacuum-sealed laboratory that our equations prefer. Enter the active galactic nucleus, or the AGN, a sprawling, luminous metropolis that represents one of the most violent environments in existence. At the heart of a distant galaxy sits a supermassive black hole, a gravitational titan millions of times more massive than our Sun. Surrounding this behemoth is an accretion disk, a swirling, flattened city of gas, dust, and captured stars, all caught in a relentless orbital grind. The friction here is so intense that the gas glows with the brilliance of 1 trillion suns, generating magnetic fields that twist and snap like cosmic whips. This disk is not just a collection of matter, it is a dense, high-pressure sea of plasma, a thick soup of energetic particles where the impossible begins to look inevitable. It is within this crowded, glowing neighborhood that our pair of smaller, stellar mass black holes was living, tucked away like two pebbles caught in a planetary storm. This environment provides the solution to a long-standing theoretical hurdle known as the no-hair theorem. In the mid-20th century, physicists like John Wheeler posited that black holes are essentially bald. Once matter crosses the event horizon, all its complex characteristics, its hair, vanish from the observable universe, leaving only the most basic physical properties behind. For decades, this suggested that a black hole merger could never wear the hair of a visible flare. However, when you submerge these bald singularities into the dense, gas-rich suburbs of an AGN disk, the environment itself becomes the hair. As the two black holes spiral toward their final union, they are not moving through a void. They are plowing through a thick medium of gas at relativistic speeds. This creates a wake, a shockwave of compressed matter that begins to glow with an intensity that the black holes could never achieve on their own. The gas acts as a witness to the invisible. It clings to the event horizons, forming its own mini-disks that are violently agitated during the final milliseconds of the merger. When the two black holes finally become one, the resulting kick, a literal recoil caused by the lopsided emission of gravitational waves, hurls the newly merged hole through the surrounding gas like a cannonball. It is this high-speed plow through the AGN city that generates the heat, the friction, and ultimately the gamma-ray burst that reached our sensors. The Schwarzschild barrier remains as a wall of darkness, but the AGN disk has turned it into a silhouette, illuminated by the very matter it was trying to consume. We are witnessing a cosmic sleight of hand where the most invisible objects in the dark are betrayed by the glow of the world they inhabit. The dense, swirling gas of an active galactic nucleus disk acts as a cosmic honeypot, a vast and viscous ocean that exerts a relentless influence on everything trapped within its borders. While a stellar mass black hole in the vacuum of deep space might drift in isolation for trillions of years, the environment inside this disk is far more crowded and far more active. As these smaller black holes plow through the thick orbital debris surrounding the supermassive center, they experience a physical phenomenon known as gas drag. Imagine trying to run through waist-deep water. The medium itself resists your motion, stealing your kinetic energy and forcing you to slow down. In the disk, this loss of energy has a singular, inevitable consequence. The black hole's orbit begins to decay, spiraling it inward toward the center of the galaxy. This migration is not a chaotic tumble, but a structured descent guided by the invisible hand of fluid dynamics. Within the disk, there exist specific regions known as migration traps, invisible orbital lanes, where the various forces acting on a black hole reach a state of precarious equilibrium. These traps are created by the complex interplay of torques exerted by the gas. As a black hole moves through the disk, it creates a wake, much like a boat on a lake, and the gravitational pull from this wake tugs back on the black hole itself. Simultaneously, the density gradients of the gas disk push from both the inner and outer edges of its orbit. A migration trap is the precise point of torque balance, a lethal and inevitable collision course, where the inward pressure of the gas exactly matches the outward push. To a wandering black hole, these traps are gravitational dead zones from which there is no easy escape. Because these traps occur at specific distances from the central supermassive black hole, they act as gathering points. It is here, in these narrow orbital bands, that multiple stellar mass black holes are funneled together. What was once a lonely wanderer in the galactic suburbs is now part of a congested, high-speed intersection. The gas of the disk does more than just move these objects. It facilitates their union through a process of orbital resonance. In the vacuum of space, two black holes might pass each other and simply continue on their way. But here, the thick gas acts like a viscous fluid that dampens their relative velocities. The gas serves as a cosmic lubricant, bleeding away the energy that would normally keep these objects apart. As they huddle together in the migration trap, the surrounding gas pushes them closer and closer, forcing them into a binary dance that would otherwise take eons to begin. This environment is a masterclass in fluid dynamics at the extremes, where the pressure and heat of the disk overcome the natural tendency of objects to maintain their distance. Within the migration trap, the black holes are effectively locked in a cage made of gas and gravity. They are held in place by the torque balance, while the constant friction of the disk material grinds down their orbits until they have no choice but to interact. This is how the ghost in the disk is born, not by chance, but by the systematic architecture of the AGN disk itself. By the time two black holes realize they are in the same trap, the fluid forces of the maelstrom have already ensured that their fates are inextricably linked, setting the stage for a collision that will send ripples through the very fabric of space-time. The final descent toward the merger of S241125N is not a gradual sinking, but a frantic, spiraling dance, where the velocity begins to approach a significant fraction of the speed of light. In these last few milliseconds, the two black holes are no longer merely distant neighbors in a gas disk. They have become a single, binary engine of pure kinetic energy, dragging the very fabric of space-time around them like a swirling viscous fluid. This is the moment of the chirp, a gravitational wave signal that rises in both frequency and amplitude, sounding a literal high-pitched alarm that resonates across the cosmos. As they touch, the individual event horizons deform and stretch, reaching out to one another until they snap together, creating a new, larger singularity in a process so violent it briefly outshines the combined power of every star in the observable universe. Not in light, but in gravitational radiation. Yet, as the two become one, the universe demands a conservation of momentum that leads to a phenomenon known as gravitational recoil. Because these two black holes were likely of unequal mass or possessed different spins, the gravitational waves they emitted during those final orbits were not perfectly symmetrical. When the merger finally settles, the newly formed black hole receives a titanic invisible shove, a kick that can reach velocities of thousands of kilometers per second. In the case of S241125N, this kick was not just a minor adjustment, it was a cosmic ejection, an impulse that sent the newborn giant hurtling through the dense medium of the AGN disk like a cannonball fired into a thick fog. As this newly merged entity screams through the surrounding gas at Mach 1000, it creates a bow shock of unimaginable proportions. Imagine a supersonic jet breaking the sound barrier, but instead of air, the medium is a superheated, dense plasma of hydrogen and helium, and instead of a metal wing, the obstacle is a gravitational well from which nothing can escape. This bow shock compresses the AGN gas ahead of the black hole, heating the medium to billions of degrees in a matter of heartbeats. It is here, in the friction between a moving singularity and the stationary gas of the galaxy's core, that the ghost begins to manifest its physical form. The kinetic energy of the recoil is converted into thermal energy with such efficiency that it triggers a localized gamma-ray burst, a flare of high-energy radiation that carves a path through the disk. This isn't the typical gamma-ray burst caused by a collapsing star. It is a shock-driven explosion, a signature of the black hole's violent displacement. The gas doesn't just glow, it shatters at the atomic level, stripped of electrons and blasted outward in a wake that trails behind the moving black hole for light years. We are witnessing the birth of a transient event that reveals the hidden architecture of the maelstrom, proving that even in the darkest, most crowded regions of space, a collision of this magnitude leaves a glowing, radioactive fingerprint that we are only now learning to read. This shockwave propagation is the bridge between the invisible world of gravity and the luminous world of high-energy astronomy, a signal that the migration trap has finally sprung, and the resulting ghost is ready to haunt the electromagnetic spectrum. The silence of the gravitational wave was broken by a flash of light that had no business being there. While LIGO and Virgo were busy mapping the invisible ripples in the fabric of space, the Zwicky Transient Facility, or ZTF, was scanning the sky for something far more tangible. Perched on the mountains of Palomar, this robotic camera acts as a wide-angle lens for the cosmos, snapping images of the entire northern sky every 2 nights. On the night of the S241125N event, it captured a sudden, sharp brightening within the glowing disk of a distant active galactic nucleus. This wasn't the slow, rhythmic pulse of a feeding black hole or the predictable decay of a distant supernova. This was a localized eruption of energy, a flare that sat exactly where the gravitational math said a collision had occurred. By matching the optical flash to the ripples in space-time, astronomers finally moved from hearing the universe to seeing it in high definition. The true nature of this ghost, however, was hidden in the electromagnetic spectrum, specifically within the realm of gamma rays. Usually, when two black holes merge in the vacuum of deep space, they are dark. They leave no trail of light because there is no matter to heat up or accelerate. But S24125N was different because he was a collision in a crowded room. As the two smaller black holes spiraled toward their final embrace, they plowed through the dense, gas-rich environment of the primary accretion disk. This gas acted as a witness to the crime. The immense kinetic energy of the merger was transferred into the surrounding material, creating a relativistic jet that punched through the disk like a needle through silk. This jet didn't just move, it screamed. It emitted a specific energy signature, a high-frequency burst of gamma radiation that distinguished it from any other cosmic event. A supernova takes days to reach its peak, but this gamma-ray ghost appeared in an instant, a sharp spike of energy that told us the recoil of the merger had turned the surrounding gas into a lethal beam of light. To understand how this light reaches our detectors across the observable universe, we have to look at the extreme physics of the photon blue shift. When the newly formed larger black hole was kicked by the uneven emission of gravitational waves, it recoiled at hundreds of kilometers per second. This sudden movement into the surrounding gas created a massive shockwave. Within this shock, particles were accelerated to nearly the speed of light. As these particles radiated energy, the sheer velocity of the source caused the light to bunch up, shifting its frequency toward the blue and ultraviolet, and eventually into the hard, piercing territory of gamma rays. This is the same principle as a siren sounding higher in pitch as it speeds toward you, but amplified to the scales of stellar mass violence. The energy we detected wasn't just heat, it is the converted momentum of the merger itself, a physical recoil that was translated into radiation that can travel for billions of years without fading. We are effectively looking at the kinetic energy of a celestial collision, stripped of its mass and rebranded as light. This discovery suggests that the migration traps within these massive disks are more than just graveyards. They are laboratories for the most extreme energy transitions in nature. The gamma-ray signature of S24125N provides a blueprint for finding more of these hidden mergers that were previously thought to be invisible. We are no longer limited to the low-frequency hum of gravity. We can now look for the glowing scars left behind in the hearts of galaxies, using the light of the gamma-ray ghost to measure the expansion of the universe itself. But as the flash fades and the gas begins to settle, a new phenomenon begins to take shape. The energy from the merger has cleared a path through the disk, leaving a vacuum that the surrounding matter is desperate to fill. This sudden vacuum is not empty for long, as the newly forged gravitational titan begins to exert a hunger that defies the standard models of celestial mechanics. We often think of black holes as patient scavengers, slowly pulling in stray gas over millions of years. But the aftermath of S24125N suggests something far more aggressive. The recoil kick from the merger hasn't just moved the black hole, it has plowed it directly into the densest regions of the active galactic disk, acting like a cosmic shovel that forces vast quantities of ionized gas into the event horizon. This is hyperaccretion, a state where the normal barriers to stellar growth are simply swept aside by the sheer kinetic violence of the black hole's movement through its medium. For decades, cosmologists have been haunted by a specific shadow in our understanding of the early universe: the growth problem. We see supermassive black holes existing just a few 100 million years after the Big Bang, appearing so massive and so ancient that they seem to break the timeline of the cosmos. How could a seed black hole, born from the death of a single star, grow to 1 billion times the mass of our Sun in such a short window of time? The answer may lie in the chaotic heart of these AGN disks and the chain merger hypothesis. If black holes are constantly merging and then immediately hyperaccreting from the surrounding disk, they aren't just growing linearly, they are experiencing a compounded, explosive leap in mass that bypasses the slow eons of traditional feeding. To understand why this is so revolutionary, we have to look at the Eddington limit, which is essentially nature's way of telling a black hole to slow down. Normally, as a black hole feeds, the infalling material heats up and radiates light so intense that the outward pressure of that light actually pushes away any new incoming gas. It is a self-regulating thermostat that keeps black holes from growing too quickly. But in the thick, pressurized soup of an AGN disk, the rules change. The sheer density of the environment acts as a lid on a pressure cooker, potentially allowing for super Eddington accretion. Here, the gravitational pull is so overwhelming and the surrounding material so tightly packed that the radiation pressure cannot escape fast enough to push the gas away. The black hole essentially chokes down matter faster than physics usually permits, swallowing the light along with the gas. This feeding frenzy is a messy, luminous affair that likely explains the lingering glow observed after the initial gamma-ray burst. The black hole is no longer just a silent ghost. It has become a glowing engine of consumption, processing the equivalent of entire planetary systems in a matter of days or weeks. As it moves through the disk, it leaves a wake of turbulence and heat, a trail of evidence that tells us the history of its birth. This process suggests that the universe has a way of fast-tracking the creation of its largest structures, using the chaotic environment of galactic centers to bypass the limits that govern the rest of space. We are seeing a glimpse into a specialized laboratory of physics where the extreme becomes the baseline. But as the new black hole stabilizes and its appetite begins to settle, we have to ask how often this happens across the vast, dark stretches of the observable universe. Is S241125 a rare cosmic accident, a 1 in a billion alignment of fate? Or is it merely the first time we've been quiet enough to hear a sound that has been echoing through the dark since the beginning of time? To answer that, we must move beyond this single event and look at the statistical frequency of these hidden mergers and what they reveal about the true population of the gravitational shadows lurking in the hearts of galaxies. Perhaps the universe is much more crowded and much louder than we ever dared to imagine. When we look at the immense census of active galactic nuclei across the local universe, we begin to realize that S241125N might not be a cosmic outlier, but rather a herald of a much more common phenomenon. For decades, astronomers operated under a statistical fallacy, assuming that the vast majority of black hole mergers occurred in the empty, silent isolation of the intergalactic void. This was the one in a million fallacy, the idea that the chances of two stellar mass black holes finding each other within the swirling chaotic disk of a supermassive black hole were so slim as to be negligible. Yet, as our gravitational wave detectors grow more sensitive, we are forced to reconcile our old models with a new crowded reality. The math of the migration trap suggests a startling degree of efficiency in the way galaxies organize their internal mass. Within the narrow, dense inner regions of an AGN disk, the gas acts as a gravitational drag, pulling smaller objects towards specific orbital resonances. It is a celestial sorting machine, a probability mapping that funnels wandering black holes into a restricted zone where encounters are not just possible, but inevitable. In these high-density tracks, the likelihood of a binary forming and merging within the lifespan of the host disk increases by orders of magnitude compared to the sparse environment of a globular cluster. We are beginning to see these disks as the ultimate breeding grounds for gravitational wave events, places where the sheer density of material forces the hand of fate. This statistical frequency raises a deeper question about the early history of our cosmos and the mysterious population 3 stars. These were the first suns to ignite in the darkness of the infant universe, massive and short-lived behemoths made of pure primordial hydrogen and helium. When they collapsed, they left behind the first generation of black holes, and it is here that the population 3 connection becomes vital to our understanding. In the gas-rich environments of the early universe, these disk mergers may have been the primary engine of growth, acting as the seeds that allowed supermassive black holes to reach their terrifying scales so quickly. If this process was the norm rather than the exception during the cosmic dawn, then the light-up mergers we see today are merely the fading echoes of a much more violent era. We are looking at a mechanism that likely sculpted the very architecture of the modern galaxies we call home. Every time we detect the ripple of a merger within a disk, we are peeking under the kilt of galactic evolution, observing the same physics that once built the foundations of the observable world. It is a sobering thought to realize that the stability of our current epoch is built upon a history of such feeding frenzies. But this statistical abundance does not just tell us about the past. It provides a new lens through which we can examine the invisible matter that holds these structures together. If these mergers are as frequent as the new data suggests, then the way they interact with their surroundings might finally provide the clue we need to solve the greatest mystery of all. Next step. The gravitational ripples from S2 41125N do more than just announce a collision. They act as a cosmic scale, weighing the invisible structures that cradle our galaxy. For decades, we have looked at the rotation of galaxies and found something that should not be possible. The stars at the outer edges move with a velocity that suggests they are being tethered by a massive, unseen influence, as if the galaxy itself were wrapped in a ghostly scaffolding of matter that emits no light. We have long called this mystery dark matter, a silent partner in the dance of the cosmos that accounts for roughly 85% of all material in the universe. But the efficiency of the merger we are witnessing in this AGN disk suggests that black holes might be playing a much larger role in this missing mass than our previous models allowed. If black holes are merging this frequently and hidden within the opaque, turbulent environments of galactic centers, we may have been undercounting the total population of these dense objects. It is a subtle shift in our understanding, but one that carries profound weight. We are beginning to see that the universe might not be filled with just a single type of elusive particle, but rather a complex graveyard of compact objects that have remained invisible to our telescopes until the advent of gravitational wave astronomy. This leads us to a question that science is only beginning to ask with real data. Where did all these ghosts come from? While most black holes are the remnants of dying massive stars, the sheer frequency of these events in active galactic nuclei invites us to look much further back in time, all the way to the first moments of the Big Bang. These are what we call primordial black holes, objects formed not from the collapse of a star, but from the direct collapse of high-density pockets in the early cooling plasma of the infant universe. If S24125N is part of a larger population of these ancient relics, then the dark matter mystery takes on an entirely different texture. Instead of a sea of subatomic particles, the missing mass of the universe could be composed of these primordial seeds, drifting through the dark for billions of years before being swept up into the frantic feeding grounds of a supermassive black hole's accretion disk. It is a compelling bridge between the largest scales of cosmology and the smallest points of infinite density. To truly understand this, we must revisit a classic debate in astrophysics, a choice between two very different candidates for the universe's hidden architecture: WIMPs and machos. For a long time, the scientific community leaned toward WIMPs, or weakly interacting massive particles, tiny subatomic ghosts that drift through solid matter without leaving a trace. But the data from mergers like S24125N is breathing new life into the case for machos, or massive compact halo objects. These are the heavy hitters of the dark: black holes, neutron stars, and brown dwarfs that lurk in the outskirts of galaxies. If these mergers are as common as the new data suggests, then the macho hypothesis, once considered a secondary theory, might actually explain a significant portion of the gravitational pull we observe. We are watching the debate refine itself in real time as each gravitational wave detection provides a new data point in the collective effort to map the unseen. It is a reminder that in the vastness of the cosmos, we find a strange kind of peace in our growing understanding of the dark. We are no longer just guessing at the nature of the void. We are listening to its heartbeat. By tracking how these black holes pair up and vanish into one another, we are slowly peeling back the veil on the most elusive particle in the universe, finding that the answer might not be a particle at all, but a silent sentinel of gravity that has been there since the beginning of time. The silence of the gravitational wave spectrum is about to be filled with a new kind of music, a low-frequency hum that our current ground-based detectors simply cannot hear. While facilities like LIGO are tuned to the final violent moments of a stellar collision, they are deaf to the long, slow build-up that precedes the crash. To capture those earlier whispers, we must move beyond the noise of our own planet and look toward the vacuum of space. This is the promise of LISA, the Laser Interferometer Space Antenna. Unlike our terrestrial sensors, which are limited by the physical size of the Earth, LISA will consist of 3 spacecraft trailing millions of kilometers behind our world, connected only by gold-platinum cubes and infrared laser beams. By measuring the minute changes in the distance between these distant points, we will be able to detect the gravitational ripples of supermassive black hole mergers months or even years before they finally touch. It is like moving from hearing only the final beat of a drum to experiencing the entire symphony as it builds toward a crescendo. We will watch these cosmic ghosts as they begin their spiraling dance, allowing us to predict exactly where and when a gamma-ray burst will ignite, long before the first photon ever reaches our telescopes. This shift from reactive observation to predictive mastery is creating a global brain of silicon and glass. In the seconds following a detection, human reflex is far too slow to capture the fleeting afterglow of an AGN disk flare. Instead, we are handing the reins to highly sophisticated artificial intelligence networks that scan the data streams in real time, acting as a digital nervous system for the planet. These machine learning algorithms have been trained to recognize the specific signature of a ghost merger, the subtle interplay between a gravitational wave and the sudden, sharp spike of high-energy radiation. Within heartbeats of a signal being flagged, robotic telescopes across every continent and in high Earth orbit pivot in unison, refocusing their mirrors to catch the fading embers of the event. We are witnessing the birth of a new era, where the sky is no longer a static map, but a live, interactive theater. It is a nightly ritual of data points and light cones, where the machines we built are finally fast enough to keep pace with the speed of causality itself. This technological leap allows us to look back at the most active period in our universe's history, a time astronomers call the cosmic noon. Approximately 10 billion years ago, the universe was a frantic nursery of creation, with star formation peaking at rates dozens of times higher than what we observe today. During this era, galaxies were smaller, denser, and far more crowded, creating the perfect environment for the kind of meat grinder physics that drives black hole mergers within AGN disks. As our sensitivity improves, we expect to find that the sky is actually crowded with these ghostly flashes, remnants of an ancient time when the cosmos was louder and much more violent. We are beginning to realize that the history of the universe isn't just written in the steady light of long-lived stars, but in these sudden, ephemeral bursts of energy that represent the final resolution of a billion-year orbit. By capturing these signals, we are effectively peering under the kilt of the early universe, seeing the raw, messy process by which galaxies grew and matured. If the Boomerang Nebula represents the cold, quiet end of a single star's journey, these AGN mergers represent the high-energy heartbeat of the collective cosmos. Every new detection is a data point that refines our understanding of how matter and gravity interact at the most extreme scales imaginable. We are still just making steam in terms of our technological evolution, yet we are already capable of eavesdropping on conversations between singularities that took place before the Earth was even a cloud of dust. There is a profound, almost mathematical elegance in the fact that we can use a laser beam in space to tell us about the internal mechanics of a galaxy on the other side of the observable horizon. It reminds us that we are not merely passive observers of the celestial clockwork, but active participants in the unfolding story of the light cone. As we prepare for this next chapter in multi-messenger astronomy, we find ourselves in a state of being comfortably terrified by the sheer scale of what we are about to discover, knowing that the silence of the past was only ever a limitation of our own ears. The transition from the violent, luminous outburst of the black hole merger to the cold silence of the deep future is not a sudden event, but a slow, rhythmic fading that defines the ultimate history of our universe. While the gamma-ray burst from S241125N provides a spectacular display of physics in the present moment, it is merely a flickering candle in a cathedral that is slowly being emptied of its light. The active galactic nuclei that currently power the most brilliant beacons in the cosmos will eventually exhaust their supply of surrounding gas and dust. The swirling accretion disks, those chaotic whirlpools of superheated plasma that we have spent so much time dissecting, will begin to thin and cool. The radiant glows of ultraviolet and X-ray energy will shift toward the red end of the spectrum, becoming fainter and more infrequent until the heart of every galaxy is occupied by a silent, dark titan. We are living in the brief, golden hour of the universe, a time when the density of matter is still high enough to foster these grand collisions. But this era of light is mathematically destined to end. As the eons stack upon one another, reaching timescales that break our brains, the stars themselves will begin to wink out. The brilliant blues will vanish first, followed by the steady yellows, leaving only the dim, huddling warmth of red dwarfs, which will eventually exhaust their hydrogen and settle into the long, cold sleep of white dwarfs. In this coming age of darkness, the black holes we have studied today will remain as the final, persistent witnesses to the passage of time. They are the ultimate scavengers of the cosmos, having cleaned their local environments of all stray matter, and they will sit in the center of dead galaxies like massive, unmoving ghosts. These objects, which we once viewed as agents of destruction, will become the only structures left with the gravity to hold onto the memory of what the universe once was. They are the final data points in a narrative that spans 1 trillion years of solitude, surviving long after the last photon from a living sun has reached the edge of the observable horizon. Yet, even these eternal sentinels are subject to the quiet, relentless laws of quantum mechanics. To understand the true end of the story, we have to look closer at the event horizon itself, where the vacuum of space isn't actually empty, but a frothing sea of virtual particles. Through the process of Hawking radiation, these black holes will very slowly begin to leak their mass back into the void. It is a process of near total absence, a thermal evaporation so slow that a black hole with the mass of our Sun would take 10 to the power of 67 years to vanish. For the supermassive monsters at the hearts of galaxies, the timeline is even more staggering, stretching toward a numerical eternity that dwarfs the current age of the universe. One by one, these titans will lose their grip on reality, shrinking and heating up in their final seconds before vanishing in a silent puff of pure energy. When the last black hole evaporates, the universe will have reached its final state of maximum entropy. There will be no more mergers, no more AGN disks, and no more observers to witness the bone-chilling cold of a space that has finally run out of things to do. In this ultimate heatsink, the story of S241125N and the ripples it sent through space-time will be truly resolved. We find a strange kind of peace in this long view, realizing that while the fireworks of the present are magnificent, they are part of a much larger, more elegant descent into a quiet that science is only beginning to map. We are stardust in our veins, currently awake and screaming into the dark. But we are also part of this slow-motion car crash toward a perfect, infinite rest. Just as the black holes will eventually evaporate into the quantum foam, our own questions and discoveries are light pulses in a vast, dark ocean. Precious because they are temporary. For now, we are still here, watching the clockwork turn, grateful for the light while it lasts. The iron in your blood and the calcium in your bones are not merely terrestrial coincidences. They are the literal debris of the celestial clockwork we have spent this journey observing. Every atom that comprises your physical being was once forged in the crushing, luminous heart of a star, perhaps one very much like those we saw being torn asunder in the accretion disk of that distant active galactic nucleus. You are, in the most profound sense, a localized collection of stardust that has gained the temporary and miraculous ability to contemplate its own origin. As you lie there now, the same gravity that dictates the graceful, lethal dance of binary black holes is pulling gently on you, anchoring you to the surface of this small, blue world. It is a stable force, an eternal tether that reminds us we are never truly adrift, even when we contemplate the near total absence of everything in the intergalactic void. The universe is vast and often appears indifferent, yet it has spent billions of years organizing itself into the very structures that allow you to draw breath and dream. Consider the journey we have taken from the initial flash of the gamma-ray burst to the silent afterglow of the merger. We began with a violent disruption, a momentary tear in the fabric of the visible, and we are ending in a state of absolute mathematical elegance. This is the natural rhythm of the cosmos, a constant transition from chaos to order and eventually to a quiet, restorative equilibrium. The atoms within you are now part of a nightly ritual of rest, slowing their vibrations just as the glowing gases of a cooling nebula eventually settle into the dark. In this moment, the staggering scales of megaparsecs and solar masses fade away, replaced by the rhythmic rise and fall of your own breathing. The universe is not just out there in the cold reaches of space, it is here, functioning with the same precision in the synapses of your brain as it does in the orbital mechanics of a galaxy. It is a thought that should bring a sense of profound intellectual safety. As we move into this final phase of our exploration, the cadence of the cosmos seems to slow, inviting a deeper sense of somnolence. The high-energy physics of the jet and the frantic spiraling of the event horizons have given way to a steady, constant peace. We often speak of the void as if it were a vacuum of meaning, but it is actually the ultimate heat sink, a place where all the energy and noise of the lived experience eventually find a home. It is silent, it is constant, it is stable. These are the qualities of the deep universe that we are now inviting into our own consciousness. Think back to the light curve of S241125N, that sudden spike of information that told us a story of two titans becoming one. That light traveled through the freezing, silent corridors of space for eons, carrying its message across the dark, only to be caught by our telescopes and translated into understanding. Now, that story is complete, and the information has been integrated into the collective memory of our species. The recapitulation of our journey is like a gentle, looping wave returning to the shore. We remember the flash, that initial burst of gamma radiation that acted as a cosmic flare, signaling a transformation in the heart of a distant galaxy. We visualize the disk, that swirling incandescent whirlpool of matter, where gravity and friction created a glow brighter than 1 billion suns. We feel the kick, that sudden gravitational recoil that sent the newly merged singularity embarking on a lonely trek through the gas clouds, a ghost in the machine of the AGN. And finally, we return to the silence. The merger is over. The waves in space-time have smoothed out, leaving behind a larger, quieter black hole that will sit in the dark for 1 trillion years of solitude. The journey from the spectacular to the serene is now mirrored in your own transition towards sleep. The void is not empty, it is merely waiting. It waits for the next cycle of starbirth, the next fluctuation in the quantum foam, and the next moment of discovery. But for now, its primary function is to provide a backdrop of perfect, beautiful silence.